Good afternoon, students. I think you can see the PPTs. Are you able to see the PPT?
Yes, ma'am.
Students,
Yes, ma'am.
you can see, no?
Yes, ma'am.
Okay, fine. Students, one more thing. Today I have shared the timetable. All of you, please make a note of it. I have swapped the computer networks as well as the DBMS subject. So DBMS will be Tuesday morning, that is on 11th morning, and my subject, computer network security, it will be on Friday. That is 13th afternoon. So my subject is the last. So before last week, I was not able to take the class as I was not well. So I have postponed. And I need to complete the syllabus, so that's why I have postponed it on Friday. Is there any issue with that?
No, ma'am. No issue.
Okay, fine. Okay, in the yesterday's class, I was discussing about the principles of congestion control. So, what are all the causes, and the cause of congestion control? So, we know that the congestion means too many sources sending too much data too fast for the network, where it is very difficult for the network to handle, channel to handle, or the people who's involved in the communication. So, if there is more people, they are communicating through the small network where a small channel, small bandwidth will be assigned, okay, where it is very difficult for the network to handle. So where it leads to loss of packets or delay in the packet arrival at the receiver end. So that's why the congestion is going to occur. So due to that, the buffer overflow, due to the buffer overflow, packet loss will be there. And we have seen the different scenarios. Alan sir, and we have seen the different scenarios. So scenario one, what it says is, it is the simple one. So where the communication is going to take place with the router, which is having the infinite buffer. Okay, that this is the point that you have to make a note on this. So where infinite buffer will be there at the router in the middle. Okay, and then the host, different hosts, 4 different hosts, they will be communicating with each other, and it is a single hop communication, means one to one. So apart from router, there is no any other intermediate devices that is connected in the network. It's a simple network with the unlimited buffers. So there won't be no delay, there won't be any packet loss since the buffer size is too large. So the throughput will be R by 2. Okay, and the delay will be finite delay. Only if there is any, if the throughput exceeds R by 2. So R is nothing but the capacity. Only if the throughput exceeds R by 2, so then only the delay will be the larger, means it will become larger and larger. So where it is nearing to the capacity, or it is nearing to the throughput, or it is nearing to the capacity of the channel. Okay, and then scenario 2, where there will be finite buffers. Okay, and then so the two hosts, they are communicating with each other. So there may be packet loss since there is a finite buffer. So since there is a packet loss, so you can retransmit the data. So suppose there is one case in scenario 2 itself. The first case, what it says is idealization, means if we think unrealistically, where only if the buffer is free, then only the packet will be sent, or else the packet will not be sent from the sender. Only when the buffer is said to be free at the router, then only the packet will be sent. So usually there won't be any packet loss. Okay, and the second case is, so here the packet will be sent only when there is timeout. Okay, only when there is timeout. So in this case, there is free buffer space. So that's why it is sending the packet. So there is no any issue with this. So that's why. So the throughput will be R by 2. So means the lambda in and lambda out. It is nothing but whatever the packets transmitted is equal to the whatever the packet that has reached the destination. Okay, in this case, where there may be a timeout. So you can observe this diagram. So there is no buffer space, so there is a packet loss. So that's why, so the packet will be retransmitted again since it doesn't get any acknowledgement. So here you can see there is a free buffer space in the router, but there is a packet loss here since it doesn't get the acknowledgement. Okay, so that's why the throughput is going to be fine because the packet has retransmitted and there is no any duplication of the packet arrival here. But in this case, what happens? The packet is going to reach the destination. The packet is going to reach the destination, but there is a timeout in the acknowledgement. So that's why unneeded retransmission will be done. So where it leads to duplication delivery of packets. So here the cost is more work for retransmission. Okay, if retransmission is done, more work is required, but there will be good put. Okay, but if there is unneeded transmission, then multiple copies of packet, it is going to decrease the throughput, means sending the same packet again and again. So the efficiency of the network will be decreased. So throughput will be reduced. Okay, and then scenario 3. So what it says, multiple senders, multiple hops, multiple paths. So there will be timeout, there will be retransmission. Okay, so that's why, so there will be throughput drop with respect to the second transmission, whichever it is, which is going to transmit at the upper queue. So first transmission, that is from A to C, and then from B to D. So what are the transmission that occurs from A to C? So there is no packet loss, but if we consider in the same time, suppose even the B is transmitted, so at that time the throughput will be equal to 0. So just this, there is a drop in the throughput. So here what the cost of congestion in scenario 3 is, so when packet dropped, any upstream transmission capacity used for that packet was wasted. Okay, so already a packet transmission is going on. So upon this, if any other transmission is happened, so the packet will be dropped, and whatever the resources that has been reserved, so that will be wasted. Okay, we have seen approaches towards congestion control, that is end-to-end as well as network assisted. In end-to-end, so there is no explicit feedback from the network, where in network assisted, so there will be explicit feedback with the help of the RM cell, where a RM cell, it can carry NI bit or CI bit. NI indicates, so no increase in the rate. So there is a mild congestion. So, and CI bit is nothing but the congestion indication. So these will be set to 1. So usually each and every packet, it is going to carry the RM cell. Okay, and RM cell, it also contains a EFCI. EFCI, which is going to, it is nothing but explicit forward congestion indication. Explicit forward congestion indication. So in order to indicate the congestion, so here EFCI is going to set the CI bit to 1. That is, will be returned by the server to the client or by the receiver to the sender with the help of the RM cell. So that's what this diagram depicts about. Okay, so and also we can see the explicit rate. So here the explicit rate, that is the ER value. So then you can increase or decrease the explicit rate. So whenever there is a congestion, you have to lower the ER value indicated by the RM cell with the help of CI bit, the congestion indication bit. Suppose if the RM cell which contains the CI bit which is set to 0, then it indicates that you can increase the explicit rate of whatever the maximum supportable rate on the path is existing. So through the same rate or through the same bandwidth, you can transmit the packet. So today we'll discuss about the TCP congestion control. So how to control this TCP congestion? So how the sender will come to know whether the congestion has been occurred. So after occurring the congestion, so what the sender has to do. So everything we are going to see today. So TCP congestion control. So here we have two different approaches, that is additive increase as well as the multiplicative decrease. Okay, so usually the sender increases the transmission rate. So transmission rate in the sense the window size. Usually the window size, especially you're going to use for the flow control. Okay, in order to do the flow control such that the congestion should not occur, such that the packet should not drop uh, in the network. So we are going to always, we should be aware of this transmission rate, and we should be aware of the congestion that is occurring. Okay, usually the sender increases the transmission rate or the window size, probing for usable bandwidth until the loss occurs. So what happens is, so the sender, so he can increase the transmission rate, suppose if there is no any loss of packets. Okay, so how you can increase? So we have an approach called as additive increase the congestion window, CWND. It is nothing but the congestion window, means the window size, by one message segment size. Okay, MSS is nothing but the message segment size every RTT until loss detected. So what we have to do, it's like trial and error method. The sender he'll be keep on. So until he find a loss, what he'll be doing? So for each and every transmission, he will be keep on increasing. He'll be keep on increasing the message segment size. Suppose first initially if he sends 2 bytes, then in the next transmission, if there is no any packet loss, he received the acknowledgement within the timeout, he can increase to 2, like he can add one more message segment size. So next time he can transmit 2 bytes, in the next transmission 3 bytes, 4 bytes, 5 bytes, so like that. So until he finds the loss of packet, he can keep on increasing the message segment size by 1. Okay, that is called as the additive increase. And multiplicative decrease, it is nothing but a cut in the size of the congestion window. So as soon as if he finds any loss at the receiver end, so what he can do is he can cut the congestion window size. Suppose the congestion window size, it has been set to 10 bytes. So as soon as if he finds that there is a loss of packets, so it indicates there is some congestion that is occurring in the network. Okay, so with the help of this loss event, so the congestion window size will be decreased in order to overcome this congestion. So here you can see tooth behavior probing for bandwidth. Okay, means, so what it indicates, so initially one particular set of packets will be sent. Okay, one message segment size, for example, 1 byte will be sent. Okay, so then what you're going to do, suppose if there is any packet loss, so what you're going to do, the congestion window size will be decreased. Okay, and then so after some time, so you'll be keep on increasing the window size. So initially it was like 1, and then 2, and then 3, and then 4, and then 5. So till 10 it's going to reach. But after 10 there is some loss of packets. Okay, so until loss you can increase the transmission rate, or you can increase the window size by 1 message segment size for every RTT, means for every transmission. So if you find any loss, then again there will be decrease. Again there will be decrease in the congestion window size. So like that you can see the seesaw. Okay, so whenever the loss occurs, you can decrease the congestion window size. Suppose if there is no any loss, you can keep on additively, you can keep on increasing the window size. So this is the graph what it shows us. It's like seesaw. Okay, so AIMD sawtooth behavior probing for the bandwidth. Okay, congestion window, the TCP sender congestion window size will be keep on increased additionally and decreased multiplicatively. Okay, so additively increase the window size until the loss occurs, then cut the window into half. Okay, so this is one approach where you can perform the congestion control using the additive increase and the multiplicative decrease. Okay, so just here we have a formula. Okay, so here just whatever we have seen in go back and or selective repeat or TCP congestion, TCP transmission. So here as usual we are having 4 different intervals. So the green indicates already acknowledged, yellow indicates sent but not yet acknowledged, blue indicates not received the data from the upper layer. Okay, so like that. So this indicates so the packet it is not usable. So like that we have the different intervals. So here's the ND indicates this is the congestion window where it's a combination of the packets which is still not yet received from the upper layer, so which also contains the packets that has been transmitted but it's not acknowledged. It contains the unacknowledged packet here. On and always we have to see that the last byte sent minus last byte acknowledged should be less than or equal to congestion window. So if it crosses this congestion window signs, it may lead to the loss of packets. This congestion window, it is said to be dynamic and it's a function of perceived network congestion. So perceived network congestion is nothing but it is going to react. It is going to means there is some awareness has to be created while the congestion has been occurred. So depending upon the network congestion, so the congestion window size will be keep on varying, increasing as well as decreasing. So if there's a packet loss, the congestion window will be reduced. If there is no packet loss, it will be increased. So like that, so that is called as the perceived network congestion. So depending upon the congestion, whether it's going to occur or not, so depending on that, the congestion window size will be decreased. So how we are going to calculate with the help of this? If the last byte sent minus last byte acknowledged is less than or equal to congestion window, then it indicates that there is no any congestion. Okay, so the TCP is sending rate. So usually it is roughly, we are going to calculate, send the congestion window bytes, wait for the RTT for acknowledgement, then send more bytes. Okay, means every time you should wait. So whether you're getting the acknowledgement, wait for the round trip time, means till the timeout. Okay, then only you have to send the acknowledgement. So the rate you can define with the help of this formula, that is the congestion window size divided by RTT bytes per second. Okay, so here we have an approach called as how to start the transmission. So we have the slow start. So slow start indicates when connection begins, increase the rate exponentially until the first loss of event. So exponentially. So first you have to like double the congestion window for every RTT. So done by incrementing the congestion window for every acknowledgement received. After receiving the every acknowledgement, you can keep on adding the segments. Okay, initially the rate is slow but ramps up exponentially fast. So initially it will be slow. Okay, detecting and reacting to the loss. So how you can able to detect? So there is some congestion or there is some loss. So how to react to this loss? So usually the loss will be indicated by the timeout. So the congestion window site usually it will be set to one message segment size. So whenever you're going to find there is a loss, so you have to set the congestion window site to one congestion window size to one message segment size. So Windows grows exponentially to the threshold value. You're going to set some threshold value. For example, 10 bytes is the threshold value that we have set. So only till that value you can set. So after that, you cannot grow. You can grow, but not exponentially, linearly. So initially it can grow exponentially, but after the threshold value, suppose if it allows, if it is having the larger bandwidth, so then one by one, one by one. So after some threshold value, till threshold value, you have to grow exponentially. So, but after that, you have to grow linearly. Exponentially means, so it is like twice the packets, whatever you have transmitted before, like one becomes two, two becomes four, four becomes eight, eight becomes 16, 16 becomes 32, 64, like that. So linearly means one, two, three, four, one after the like that, one by one. Okay, and also loss indicated by 3 duplicate acknowledgement, and we are going to call it as the TCP Reno. So if there is a duplicate acknowledgements, you will be keep on receiving from the receiver side. That is 3 duplicate acknowledgement. Then fast, you can able to identify very fast that there is a loss of packet. So at that time, Duplicate acknowledgements indicate network capable of delivering some segments. So congestion window is cut in half, window then grows linearly. So at that time, the congestion window size, you have to set it to half and then you have to grow linearly. Okay, so TCP Tahoe. So TCP Tahoe is nothing but, so it always means, what it says is always set the congestion window to 1. So whenever there is a timeout or whenever there is reduplication of packets, means acknowledgements. Okay, so here you can see when should the exponential increase switch to linear. So here you can see 1, 2, 4, 6, 8. So like that. So there was some exponential increase in the transmission rate of sending the packets. So as soon as it finds a threshold value, then you have to go linearly one after the other. You can see in this diagram. So threshold value we have set it to 8. So after that, what you have to do is you have to go linearly. This is one case. And in the other case, when you have to go linear in the sense, so whenever, so suppose if there is a duplicate acknowledgements, you have received 3 times one after the other immediately, even at that time you have to grow linearly. So here there is a dropping of packets. So since there's a dropping of packets, you're not able to receive the acknowledgement. So that's why here the graph has been moved from 12 to 9, means the throughput is reduced here. Performance is reduced. So at that time you have to grow linearly. Okay, and after the threshold, again you have to grow linearly. Okay, so when you have to reduce the transmission rate from exponential to linear is, so when it reaches the threshold value, or else, so whenever there is a drop of packets, so at that time you have to move linearly. So when congestion window gets half of its value before the timeout, so during that time, so half, it indicates congestion window value. Suppose it has been decreased from 12 to 6 or below that, then it indicates that there is a drop of packets. So at that time you have to move linearly. Okay, implementation. So you can vary the variable threshold value also. If there is more number of packets that is dropping, you can also reduce the threshold value. Slow start threshold value. Okay, so in slow start we'll be having the variable SS threshold value. On loss event, the SS threshold value will set to half of the congestion window just before the loss event, because here it has initially it was set to 8, and since there is you are moving linearly one after the other after reaching this threshold value. So as soon as there is a drop of packets, you have reduced the congestion window size to half, means the threshold value to half, that is 8 or 6 or 4, means you have reduced the threshold value, and then you're going to send the packets one after the other linearly. Okay, so here we have, so slow start, okay, congestion avoidance and fast recovery. Here we can see for TCP congestion control. So here we have a finite state machine with 3 states. One is the slow start, second one is the congestion avoidance, and third is fast recovery. Suppose first slow start means you're going to, in the beginning, you're going to start slowly one after the other. Okay, congestion window size is 1 message segment size, and threshold value are going to set 64 kilobytes, and duplication, initially the duplication acknowledgement count will be equal to 0. So this is the starting state. Okay, this indicates it is the starting. So and then as soon as there is a duplication acknowledgement, as soon as there is an increment in the duplication acknowledgement, means multiple duplication acknowledgement if you receive, then you have to go to the state called as slow start. Or suppose if you are starting your transmission newly, so there is a new acknowledgement you have received, then you have to increase your next transmission. So initially it was first segment, and second time it was you're going to increase by 1 more message segment size. At that time the congestion window size will be equal to congestion window size plus 1 message segment size. So duplicate acknowledgement count will be equal to 0. Duplicate acknowledgement count will be equal to 0 at that time. Okay, so and when you will be in the slow start, so whenever there is a timeout, so at that time the threshold value that should be reduced to congestion window divided by 2. So if the congestion window, if you are going to set to 64 kilobytes, Okay, and the congestion window size, suppose if you have increased to 8, then it should be reduced to 4 or 6, so like that. Okay, and then the congestion window will be equal to one message segment size, and here you have not received any duplicate acknowledgement, only the timeout has been done. Okay, so here transmit the new segment as a load, and here the retransmission is retransmit missing segment. So here there is a missing of retransmission segment. Okay, and when we have to go to the state called as the congestion avoidance state. So suppose if the congestion window size is greater than or equal to the threshold value. So at that time, you have to go to the congestion avoidance state because it may lead to congestion, or you're going to receive a new acknowledgement. Okay, where the congestion window size is equal to congestion window plus the message segment size into message segment size divided by congestion window, and the new duplicate acknowledgement count is equal to 0. So whenever the congestion window size is greater than or equal to the threshold value, so at that time we're going to congestion avoidance. Okay, and suppose if there is a duplicate acknowledgement, and if the duplicate acknowledgement is keep on increasing, you can go for congestion avoidance. And if there is a timeout, what you have to do, you have to go for slow start state. So at that time, what it's going to do, at that time threshold value will be reduced to half, and then congestion window you're going to start from the slow start, that is 1 as the message segment size, and duplicate acknowledgement is equal to 0. So retransmit missing segment. So when there is a timeout, you have to do the retransmission. Count, it is equal to 3. It indicates that there is a packet loss. So even at that time, the threshold value should be equal to reduce the congestion window. And then what you have to do is, so the congestion window size is equal to 3 times the message segment size. 3 times the message segment size. Okay, so during that time retransmit the missing segment, but fast recovery can be done because since you are sending the duplicated acknowledgement again and again within the timeout, this happens within the timeout. Okay, then the threshold value should be reduced to congestion window by 2, and the congestion window should be equal to SS threshold value plus 3, because 3 times the duplication acknowledgement it is sending, because already it has sent the 3 segments, but you are not receiving the acknowledgement for those segments, but you are receiving the duplicate acknowledgements, indicates that there is a packet loss of the previous packet. Okay, that's why plus 3 here. Okay, so like this, and the same thing, if there is a duplicate acknowledgement, if there is a duplicate acknowledgement, so again the congestion window will be equal to congestion window plus MSS, means the message segment size. If there is a new acknowledgement, and if the congestion window is equal to threshold value, it was in the fast recovery state. Okay, means whenever there is a duplicate acknowledgement arrives, or else if the duplicate acknowledgement arrives immediately one after the other, that is about 3, then you have to go to the recovery state called as fast recovery state, and only this is with respect to before the timeout. After the timeout, it will go to the slow start state. Suppose if the congestion window size is equal to threshold value or greater than the threshold value, it will go to the congestion avoidance states. Suppose if there is a duplicate acknowledgement and duplicate acknowledgement count is equal to 3, then it will go to the fast recovery state. Okay, so congestion window is equal to threshold value, so duplicate acknowledgement is equal to 0. So even at that time, you have to go for the congestion avoidance state. So in the same way, here also timeout and then threshold value. So there is a timeout, so threshold value should be decreased. Congestion window, you have to set it to 1, and since there is no duplicate acknowledgement, so just you have to retransmit the missing segment. Okay, and then if it is in the slow state and there is a duplicate acknowledgement equal to 3 within the timeout, okay, threshold value should be reduced, and then congestion window value will be equal to, so whenever there is a 3 duplicate acknowledgements, then the congestion window size always it will be equal to the slow start threshold value plus 3. plus 3. You should keep in mind. So usually at the initial state, or usually when you want to transmit the new packet, or usually when there is a timeout, you will be in the slow start state. So you will be going to the congestion avoidance state. So whenever the congestion window is greater than or equal to threshold value, or whenever the congestion window is equal to the threshold value, then only you will go for the congestion avoidance state. And when you will go for fast recovery status, whenever you're going to get the duplicate acknowledgement, whenever you get the duplicate acknowledgement is equal to 3, then you have to go for the fast recovery states. And always, whenever the duplicate acknowledgement is equal to 3, the congestion window size will be always equal to the slow start threshold value plus 3. Okay, so this shows the timeout process and the new acknowledgement. So next, throughput. So generally the throughput formula it is given by, so average TCP throughput as function of window size and the RTT. So by ignoring the slow start, so I assume always the data has been sent. So the window size, so where the loss has been occurred, so that window size is measured in times of bytes. So here the window size it is given by 3 by 4 of W. Okay, so on the average throughput it is given by 3 by 4 of W per RTT. So it is given by, means to calculate a TCP throughput, you need the window size as well as the RTT. So the formula is given by 3 by 4 into W divided by RTT in bytes per second. So here there is an example. So suppose if the TCP, whatever you are implementing over a long channel with fat pipes. Okay, fat pipes means the long channel with the larger bandwidth. So for that, if 1500 byte segments are there, that means the message segment size, and then 100 millisecond is the RTT. So so the throughput that is required is about 10 Gbps, where it requires the window size about 83,333. Suppose the throughput you have to calculate with respect to segment loss. In the previous case, there is no segment loss. But here with respect to segment loss, L, then the TCP throughput it is given by 1.22 into the message segment size divided by RTT and the square root of L. So usually to achieve 10 Gbps throughput, need a loss rate. So loss rate after some calculation. So we are going to get the loss probability L, it is given by 2.10 to the power of minus 10. So this is a very small loss rate because it is to the power of minus 10. Okay, so just this is the formula. So in order to calculate the TCP throughput with respect to loss probability, the previous one there is no loss probability, just if they have given window size and the RTT, you can calculate the average TCP throughput. Suppose if there is a loss probability, then you have to apply this formula. 1.22 into MSS divided by RTT into square root of L. Okay. Now we can see new versions of high-speed TCPs. Okay. So what is this TCP fairness? So the the fairness is nothing but whatever the bandwidth that is available, it should be equally distributed to all the people that is involved in the network, all the hosts that is involved in the network. For example, if there is k TCP sessions, okay, k TCP sessions means if the 10 TCP people or 10 different hosts is communicating, then whatever the capacity, for example, 50 is the capacity, then 50 divided by 10 will be the rate for each and every people or each and every host that is involved. Okay, if k TCP sessions share same bottleneck link of bandwidth R, so each should have the average rate of R by k. So average rate, how you can define with respect to TCP fairness is equally the bandwidth should be shared among all the people. So if there is 2 hosts here, okay, and R, let us consider it is about 10. Capacity is about 10 bytes. So 10 divided by 2. So means for each TCP connection, 5 bytes has been reserved. So like that. So that is nothing but the TCP fairness. Fairness is nothing but so equally distributing the bandwidth for all the hosts that is there in the network. So why TCP fair here? Because so 2 competing sessions. So what it says is additive increase gives slope of 1 as throughput increases. If there is additive increase, so then the throughput is also increased. If multiplicative decrease, then it decreases the throughput. proportionally. See, if you have given the equal bandwidth, then so it will be equally shared among all the users so that they can effectively transmit the packet. So what this dotted lines indicates is, so this is the slope value you're going to get. So this indicates the equal bandwidth share between the two hosts, the connection 1 throughput R and the connection throughput R. So if we consider this as 2 and this as 2, so equally the bandwidth has been distributed. So here there is a congestion avoidance. It will go to the congestion avoidance state because there is additive increase. And here there is a loss of packets, loss of window, because we have to do the congestion avoidance. When you will go for congestion avoidance, if the congestion window size is greater than the threshold value, so whenever it increases, usually the drop of packets will be there. So that indicates there is a loss. So what you have to do, decrease the window size by a factor of 2. Okay, so again there is a congestion avoidance due to additive increase. Okay, so that's why what you have to do, you have to decrease the window size by a factor of 2. Means what it indicates, what this seesaw, what it says is, so whenever there is it is in the congestion avoidance state, it indicates that there is some congestion may occur or may be occurring. So at that time there is a loss of packets, so immediately decrease the congestion window size to half. Okay, so next, fairness and UDP, fairness parallel TCP connection. So suppose, if we consider TCP, so multimedia applications often do not use TCP, do not want rate throttled by congestion control. So usually the multimedia application, so it doesn't make use of the TCP because the audio and video at the constant rate tolerate the packet loss. So here it can't vary. So in the TCP, in the previous examples and also we have seen that there is a variation in the congestion window size. Sometimes it will go up, sometimes it will go down. Suppose if it crosses the threshold value, the congestion window size has to be decreased. Suppose it doesn't cross, then you have to increase the congestion window size. So there is a variation. But for multimedia, usually the audio and the video messages, they need the synchronization. So they need the constant rate. So with the help of TCP, it's not possible. So instead, we are going for UDP, send the audio or the video at the constant rate and tolerate the packet loss so that the packet loss can be tolerated. Okay. So the fairness parallel TCP connection means the fairness is nothing but the constant equally distributed bandwidth. Okay, so the application can open multiple parallel connection between two hosts. Okay, if two people they are communicating with each other where they are using the multiple web browsers, if multiple web browsers are existing, the multiple parallel connection that is required between the different hosts. Okay, so example, the link of rate R with 9 existing connection. New application asks for 1 TCP gets rate of R by 10. New application asks for 11 TCPs get R by 2. So like that means if the number of TCPs increases, then the capacity also decreases. Capacity decreases means where you can use the parallel TCP connection is in case of web browsers if they want to do the parallel communication with the other end of people or other hosts. If they parallelly they need to communicate with each other, then they can go for TCP connection. So fairness in UDP can be achieved in multimedia. Fairness in TCP can be achieved in the web browser application. Okay, this completes your second module. So till now we have discussed about multiplexing, demultiplexing, reliable data transfer, flow control, congestion control, and implementation of the internet in UDP and TCP protocol. And then so these are the things we have discussed in this module. This is really a large module, very vast. So I take some extra time to explain this because the concepts are very important. So in the next class from tomorrow, we'll start with the third module. So till next Thursday, so whatever the topics I'm going to discuss, we'll be having for your internals. So Friday, there will be second internals. That is on 13th of November, we'll be having the second internals. So till that particular time, so whatever I'll be discussing, so that will be there for your internals. Okay, students. So have you understood the second module. If you have any doubts, anything, you can ask me. Okay, now we'll wind up the session. Thank you so much.